Hi, I'm Mark Stephenson with the AVS lab at the University of Colorado Boulder. Today I'll be presenting autonomous satellite inspection in low Earth orbit with optimization-based safety guarantees. So what's the motivation for autonomous inspection tasks? Well, we've seen a growth in the number of proposed or current missions that aim to do rendezvous proximity operations and docking or in-space assembly and manufacturing type activities. And before you do some activity that requires interaction between two spacecraft, it's good to understand the spacecraft you're interacting with. This might mean you need to figure out where the docking port is before you're preparing to dock. This could mean that you're trying to identify damage on an asset before you're servicing it. Perhaps you need to fully identify the targets you can figure out how to latch onto it before you deorbit it. Or maybe it's just an unfamiliar space asset that you want to know more about. Of course, any of these activities are risky. They have the risk of two spacecraft colliding with each other, which is generally regarded to be a pretty bad outcome. So specifically, we're looking at the problem where we're trying to inspect all of the illuminated faces of the RSO while minimizing fuel use. So our first maximization term is, of course, maximizing the number of inspected faces. And to inspect them, it requires a few things. We need to have a good instance angle from our camera bore sight of no more than 30 degrees. We need to be close enough to our spacecraft, and each facet needs to be illuminated with a sufficient level of sunlight and no eclipse. We're also trying to minimize fuel use. So here we penalize fuel use by some coefficient alpha times the amount of fuel we use. The actual fuel is used through the control that we have in this problem. We're able to do impulsive burns in an arbitrary direction, followed by passive drift. And finally, we need to maintain safety. We aren't allowing collisions or any violations of a keep-out radius at any point during the mission. So to simulate this, we're using BSK-RL, which is the lab's tool for environments for satellite reinforcement learning. This takes Basilisk, which is the in-house simulation framework, and wraps it in Gymnasium, which is a standard reinforcement learning environment interface, and that yields BSK-RL, which is configurable for satellite RL research. This inherits the best of both Basilisk and Gymnasium, so we get modular spacecraft and environments and high-fidelity simulations from Basilisk, but then we also get our compatibility with all our major reinforcement learning libraries through Gymnasium. And you can check out BSK-RL online right now and see a number of the types of problems that we're able to pose with this package. Returning to our original problem, let's look at the specific MDP that we're using. Our observation space consists of information about our relative position and velocity in the hill frame relative to the RSO, how much delta V the inspector has left, the orbit that we're in, where the sun is, and how long we have until the next eclipse, and how much we've inspected different regions of the satellite. Our action space reflects the control that we have in this problem, so that means that we get to select a delta V and drift duration. And our reward is yielded by completing the task, so we're going to gain reward for inspecting new points, with a maximum of 1 reward for inspecting every point. We also will get a completion bonus if we successfully hit a 90% threshold, and even though the number seems a little low, that's to handle cases where points that are on the very edge of the illuminated region may only be instantaneously illuminated, so it's unfair to require inspection of something that may only be illuminated for a few seconds out of the entire orbit. We yield a fuel penalty parameterized by alpha for every burn, and we also have a failure penalty parameterized by beta. We'll just set that to 1, as will the completion bonus be 1. The transition function is deterministic, with transitions given by the high-fidelity simulator. The step duration in the semi-MDP formulation is given by the drift time that we've selected, and the terminal failure states are going to be collision, running out of fuel, or being too far from the RSO, and then success, of course, is also a terminal state, but a good one. So let's start by looking at unshielded tasking. So this has no safety guarantees yet. We start by training 24 policies, each for 48 hours on 32 cores, using an implementation of proximal policy optimization that we've slightly modified to handle variable step durations. The hyperparameters we searched across include the discount rate, the learning rate, and most importantly, that fuel penalty alpha. So starting off, we are going to look at the reward that each of those policies gained over the course of training, as well as the amount of delta V those policies used. In purple, we have policies with a low fuel penalty, whereas in yellow, we have policies with a high fuel penalty. And we can see that in general, the low fuel penalty is going to have used more delta V. The high fuel penalty is going to have used less delta V, as we would expect. And unsurprisingly, the more we limit the amount of delta V that the policy can use, the poorer the reward is. This is reflected in the completion of the tasks. We see that both the percent inspected and the time it takes to succeed at the mission when it does succeed is low when you have a high fuel penalty, but having a low fuel penalty allows you to inspect all of the points more easily and more quickly. Let's take a look at a performance benchmark for one of those policies that had alpha equals 0.2. We take 1,000 trials and evaluate the policy Unshielded. And this is over a variety of inclinations and ascending nodes. We see that many of the cases, as much as 80% of the RSO was illuminated at some point. But in certain cases, like SSO-like cases, we may see illumination fractions that are as low as around 30%. This policy generally performs well by itself. We see that it has an occasional number of cases where it has non-critical failures, like taking too long or using too much delta V. But we do have about 0.3% of cases where the RSO and the inspector collided. This is a bad thing, and this shows why we're going to add some safety guarantees later on, because while the policy can learn pretty well to avoid this negative terminal state, it does not perfectly learn to avoid that state. We can also look at the impact of that fuel penalty parameter. When we compare to another benchmark of an even lower fuel penalty case, we see that alpha equals 0 yields a policy that completes the task very quickly, but with a higher amount of delta V. And really this implies the existence of a Pareto front between delta V usage and inspection task duration. That's something that we want to look farther into in the future. Looking at some individual cases, we can start with an unshielded high illumination case. So this is going to be running the policy open loop for a case where about 75% of the points are inspectable at some point. We can see, of course, that in periods of eclipse, we don't increase the number of points that we're inspecting because no points are inspectable. We can also see in this case, much of the delta V can be attributed to those first two large maneuvers that were used to get close to the RSO, because in this case, the inspector was randomly seated to be far away from the RSO. Here we have a video of a case similar to that one, where we have a high illumination fraction. The yellow points are ones that are currently illuminated enough to be inspected, and green points are those points that are actually inspected. We can see as we go into eclipse, all of the points become gray that have not been inspected because nothing's inspectable. But as we come out of eclipse, the inspector is there ready to track that yellow area to inspect more points as they become available. On the inspector, we can see the true trajectory line in blue, as well as a gray passive trajectory line, which would be the trajectory of the satellite without any further control. Moving on to an unshielded low illumination case, so this is like a sun-synchronous orbit type of case, we can see that once again, the satellite performs well. We don't have any areas in eclipse on this case because we're in SSO, so the sun is always exposed to at least some parts of the RSO. And we can see that the policy has figured out which side will be illuminated in these cases, and tends to stay on this side for the duration of the task. Once again, we have a video of a similar SSO type case. We're going to get two angles of this. The first one is looking at it towards the illuminated side of the SSO, so we can see how those yellow points become green over time. And then in the second case, we get to see how the inspector is moving relative to the RSO. Up in that upper left-hand corner, if you haven't figured out yet, is a view of what the inspector is actually seeing on the RSO. So, as I alluded to a few times, collisions between our spacecraft and the spacecraft we're inspecting is generally regarded to be a very negative outcome. So, to avoid this, we introduce a concept known as shielded reinforcement learning, which is a way of ensuring safety guarantees in with our policies. So, what is shielding? It's a fairly simple concept. We say we have some action space, and we only want to allow only allow actions that are in some safe set, which we define as that the next state, or perhaps no future states that this action will lead to, could be unsafe. So in this type of continuous control situation, what it often looks like is the shield will figure out what actions are safe, and then we select the policy's most favored action that is within that safe region of the action space. In particular, for this case, we can pose that as an optimization problem, where we minimize the deviation from the most desired action while maintaining safety. So that minimization is the objective of our optimization. We want to minimize the change between our selected delta V and the delta V that is deemed to be safe. We need to obey the impulse limit that our satellite has, so no impulsive burn can be more than 1 meter per second. And we want to avoid collisions over some evaluation horizon, which we're somewhat arbitrarily picking to be 2 orbits. Of course, we want to be safe forever, not just for 2 orbits in case our agent picked perhaps a very long action, or if it selected an action that then would eventually lead to a collision, and if we entered safe mode or something like that, we would then be on a collision course with no means to overcome that. So this last constraint ensures safety beyond the horizon that we're explicitly checking for at some delta t. And how this works is that we can enforce that the servicer is always either in a passively periodic orbit with the RSO, or an orbit that has some secularly increasing in distance term. So we can now run that same benchmark, but introduce the shield with the policy. In this case, we're using a 10-meter guaranteed keep out, and we can see that it worked. Collisions are eliminated. We had 0 collisions, whereas previously 3 of those 1,000 cases resulted in collision. The shield is not particularly intrusive either. We see that only 5.9% of actions had any sort of intervention. In most of those interventions, we're looking at things on the order of 1 millimeter per second. The evaluation time is also quite good, and on average it takes 0.73 seconds to evaluate just on my laptop. But keep in mind that we're making these decisions somewhere on the order of every 500 to 2,000 seconds. So even with increased evaluation times on a spacecraft processor, you should be able to find the time to evaluate the shield prior to taking a task. And recall that if you don't, the previous shield evaluation has already guaranteed you're in a passively safe orbit, so you could delay making a new action if for whatever reason you were unable to find a safe action fast enough. We can also see that the shield does not impact the delta V or duration of the policy very much. The delta V is only slightly higher than the 2.9 meters per second of the unshielded policy, and the duration is actually slightly shorter at 3.02 orbits instead of 3.04 orbits. Let's look at a specific instance using the shield. And in this case, we're setting the shielded keep out radius to 100 meters. That's really another benefit of this sort of shield. We aren't stuck with some keep out radius that was learned by the policy. Instead, we can set any arbitrary keep out radius. So in this case, perhaps we're earlier on the mission. We want to characterize the RSO better before we start getting closer to do perhaps a, preparing for docking or whatnot. And we can see that the task is completed very well. We end up with a policy that never violates the 100-meter constraint while still completing the problem. In conclusion, we've shown that RL can provide a closed-loop solution for inspecting a spacecraft, leveraging the natural relative motion of the spacecraft. We get analytical safety guarantees by formulating and solving an optimization problem at every decision that we make, really making this viable for actual use in space. Thank you for listening to the presentation, and we'd be happy to field any questions.